Welcome to our numerous WebKit SIRS epidemic modeling web app. This is instructional video 3. In this video, we will select the stochastic mode. We will show you how to run this so you can generate a bimodal fail-to-invade/burnout distribution. We will show you how to change the parameters to generate stuttering transmission chain distributions and save the results for more detailed analysis. But before proceeding, you should be familiar with the run mode implementation, which you can find on our instructional video 1. So here we are. When we open the app, we're on run mode. And we'll just review that if you press the start, you'll see a simple run mode simulation. The stochastic mode is based on a stochastic version of the deterministic continuous time SIRS model. This is the discrete time version of that model. It's actually very simple, and what it says is that the number of individuals in each of the disease classes S, I, and R is equal to the number of individuals in that class in the previous time period minus the number that made the transition out to the next disease class plus the number that came in from the previous disease class. The parameters PRS are transition proportions in the discrete time model or transition probabilities in the continuous time model, and are based on the concept of a flow rate among the various disease classes, the row XYs, where X and Y are either the SI or R disease class. The stochastic version of this model is almost identical to the discrete version, except instead of calculating proportions that leave and come from the various related flow classes, we're now calculating the proportions based on a binomial drawing. That is, each individual has a random probability based on this PSI that we define over here of making the transition or not making the transition in each time step. And this notation is meant to mean a binomial drawing of X individuals with an expected number Px that will make the transition. There's also critical value associated with SIRS models, and this value, called R0, is the ratio of the transmission rate to the recovery rate. The transmission rate is made up of two parameters: beta, the force of transmission, which is actually in the stochastic setting the probability of transmission per contact, and kappa 0, which we have talked about in the continuous time model, is interpreted as effective contacts rather than actual contacts, where an effective contact means a contact with transmission, which means that then, without loss of generality in our model, we can just select beta equal to 1 if we interpret kappa 0 in this way. R0 is called the basic reproductive number, and it is interpreted as the number of new cases. The original or index case, also known as patient 0, will on average infect at the start of the epidemic. So let's select now the stochastic simulation mode. These are the default parameters that will come up in this mode with a constant contact rate. The baseline contact rate here is 1 and the recovery rate is 1/2, so R0 is equal to 2. Okay, let's press the start and start the simulation. In this case, we set to do 100 runs. We're already on run 85. As we watch these runs come in, we see something rather interesting. Some of the runs, there's a fail for the epidemic to get started. We call that a fail to invade. Or if the epidemic gets started, then we get the normal epidemic curve, although there's some variation exactly when the epidemic burns out. Let's wait for the completion of these 100 runs, and we can see the typical distribution that we get for the extinction time histogram when we implement 100 runs. If we repeat this, we'll get 100 runs again, except the distribution will look slightly different because of stochastic effects. Now let's look at the extinction histograms for different values of R0. So here we have R0 equal to 1.6, and the fail to invade probability that we get will decrease with the value of R0. So as R0 increases, this component will get smaller, and this component, which is the epidemic burnout, will get bigger. Let's now look at R0 equal to 1. In this case, we're right on the edge of whether an invasion will take place or not. And if an invasion takes place, then because R0 is equal to 1, this is a rather slow-burning epidemic, and by time t equal to 100, those that have invaded have not yet burnt out, as we can see from this prevalence curve. But if we go for long enough, we'll get a distribution at the end of around the burnout time that looks like this. And finally, let's go to an R0 which is less than 1. And in this case, we get what are called stuttering transmission chains of various lengths. Most of them don't make it beyond one time period, but sometimes the epidemic will persist and kind of stutter along until it finally burns out. Once we've made our runs, we can download the CSV file. And here we see that when we download the CSV file, all the information related to the values that we choose for the parameters and so on are in the heading of this file, plus the simulation results over here that are used to construct the mean and standard deviation curves. And then below this we will find the histogram details that will tell us exactly how many runs went extinct after one time period, 2 time periods, and so on, so that we can study this distribution in detail if we so desire. This is the end of video 3, and I thank you for your attention.